Hi, welcome to this short video looking at displacement time, velocity time, acceleration time graphs. Okay, we have young Bob here helping us as always, and Bob has his bright green running trainers he's just bought from Asda, and let's let him try them out. Now we're going to assume Bob here travels from this point to his armchair, his favourite armchair, and we're going to make the assumption that he travels at a steady speed, so at the same speed. Okay? Now that is going to look like a straight line on this graph. Now let's just be aware here, if Bob had travelled slower, same steady speed, steady speed, steady speed, slower, we would have a much shallower gradient. If Bob had travelled faster, we would have a much higher gradient. A really powerful tool to try and get your head around this and support you in where does my line go, what sort of gradient do I have, is take 1 unit of time on your graph, say 1 second. You can see here, for that 1 second, the distance travelled is tiny. Whereas, if we look up at the blue one here, for that same 1 second, the distance travelled is much greater than here. Okay? So, that's a really powerful tool that we can use to compare different graphs and look at relative speeds. Okay, so he's travelled steady speed along to his favourite armchair. He's then going to have a rest, so as time is going along, distance isn't increasing or decreasing, he's then going to move at steady speed back here. Now even though he's ending up where he started from, we can't have negative distance, so again that's going to be a straight line, assuming steady speed. Okay, now this idea of even though he's gone back to where he started from, graph's still going up, we can't have negative distance, is a kind of strange one, and a much more useful terminology is displacement. Displacement is the distance from a fixed point or origin. So let's look at displacement time for the same journey. Bob travelled here, yeah, it's exactly the same. No difference there, he's having a little rest. Now, displacement, distance from this fixed origin point here. As Bob then travels back, his displacement is decreasing until he ends up with a displacement of 0. He is back where he started. Okay? Now, if we, let's just change the origin, shall we? Let's make the origin where Bob's armchair currently is. Okay, so let's move Bob to his armchair, and that's now the origin. If Bob has the same first part of the journey, up here, steady speed, has a little rest, back here, we would see the same sort of graph, has a little rest, back to where he started. Now, displacement time, as displacement can be negative, if Bob at steady speed travels over to here, remember we have this as the positive direction, so his displacement is actually going more and more negative. Let's just say he has a little rest again, and then travels back to where he started, here. So we can see he's gone steady speed away from the chair, then he's gone and had a little rest at the end, come back, and then in this section here, gone away from the chair, had a rest at the end, and gone back to his chair. Now, if we look at these down here, speed is distance over time, velocity, this is the one that we're going to use, is displacement over time. We can actually find his velocity by taking his displacement over a section of time. So all we would do here is say for his initial part of the journey that took him 10 seconds and was 20 meters. Okay? all we would do is say his velocity is displacement of 20 meters divided by speed time of 10 seconds. It is 2 meters per second. That would be his velocity for that section. Okay, now let's look at some other graphs. Right, we're now looking at speed time. And over here we have Cedric on his jet ski. He's been to a health and safety course and is now fully aware that you must wear a green hat whenever you're on your jet ski. So, what's Cedric gonna look at here? Well, we've now got speed time. So let's just think carefully about what happens here. We've got this section, which is a straight line. So speed is increasing at a steady rate. So he is accelerating. He's starting from 0. Speed at this origin point here is 0. He's accelerating and getting up speed here. So from here to here, he's accelerating. When he reaches this point here, his speed does not change as time is ticking along, so he's then reached steady speed. At this point here, as you can see, his speed starts to decrease, so he is decelerating, where he can stop there and have his nice cup of tea. Yummy. Okay, so here, this speed increasing at a constant rate means we have constant acceleration. Here, speed decreasing at a constant rate means we have constant deceleration. Now, similarly to before, we can use equations to work out things from our graphs. Speed is distance over time. Distance is speed times time. So if we look here at this middle section, distance travelled is the speed of 10 meters per second that he's travelling at, 10 meters per second, multiplied by the time it takes him, which is 13 seconds. So the distance travelled in this section is actually 130 meters. So we can see from this equation that the area under a speed time graph gives us distance travelled. So for this section here, obviously distance travelled would be a half times the speed of 10 times the time of 5, so that's 25 meters. And for the other section, we have a half of the speed of 10 times the time of 2, which gives us 10 meters. So the total distance that young Cedric has travelled is 165 meters. So that's very useful. Key point there, that the area under a speed time graph gives us distance, and that's what we can see from this little equation here. Okay, so we're looking here at speed time. What's that, Cedric? You want to go back home? Okay, so but the same as with distance, if Cedric's travelling this direction, we have taken this direction as positive. We need some way of showing that. So similarly, distance time and speed time don't have direction. They are not vectors. Displacement time and velocity time do have direction. Velocity is a vector because it has magnitude and direction. So let's have a look at this little graph here and see what it's telling us about Cedric. Okay, velocity is increasing at a steady rate, so we have constant acceleration for this section of the journey. So he's starting here, accelerating to here, where he's then maintaining a constant velocity, because here velocity is not changing as time is ticking along. He's then decelerating here. This point here at 14 seconds, he's stopped. His velocity is 0. What then happens, this section here shows us that his velocity is becoming negative. It's becoming negative at an increasing rate. So he's stopped, is accelerating in this direction. When we get to the key bottom point here, his velocity has reached its maximum for that part of the journey, and for this section here, he is then decelerating. Okay, so what happens is he's accelerated, steady velocity, decelerated down to 0, accelerated back in this direction, reached a maximum velocity of 5 meters per second, and then decelerated back to 0. Where does young Cedric end up? Well, the same as the distance under the distance is the area under a speed time graph. Displacement is the area under a velocity time graph. So we could work out the area of each of these sections. Now these three here I'm going to do in blue would give us a positive value. Because we have direction here as well as magnitude, the area of this section here would give us a negative value. And what we would do is we would work out the area of each section. So we would work out the area of the positive sections, which gives us 95 meters, and the area of the negative sections, which is 15 meters. So the actual displacement at the end of that journey of Cedric would be, he would end up, let's move him along a bit, he would end up 80 meters away from where he started. Okay, the only other thing I need to point out here, using this equation down here, acceleration is, as we see before, is the change in velocity over time. So we can find the acceleration simply by saying, look, okay, from this point A to this point B, the change in velocity has been 10 meters per second over 5-second period of time. The acceleration is 2 meters per second per second. Right, so to recap, key points are: on a displacement time graph, oh, Bob's still having a rest. Good, I think he's fallen asleep. Displacement time graph, we can go positive and negative. Displacement is the distance from a fixed origin. On a distance time graph, we can only go positive. We cannot have any lines going downwards because we cannot have negative distance. On a speed time graph, we can have speed going positive and down to 0. Speed cannot be negative, does not go below the axes here, and the distance travelled is the area, as we saw here, of 130, 25 and 10 meters. Distance travelled is the area beneath a speed time graph. The displacement is the area beneath a velocity time graph, and finally acceleration is the change in velocity over time. As with all mechanics, please look at your answer. Does it make sense in relationship to the question you've been asked? Okay, thank you for listening.